See you later, man.
Test 1, 2, 3. I hear it here. We can hear. Great. Any questions from last time? There's a handout that I posted just before class that hopefully you can have in front of you. And the other issue is so we're splitting the class into 2 groups that should be posted. And sorry, the exam, sorry, the class. We're splitting the class into 2 groups for the exam. And 2 groups are Spalding Life Science, SLS, and New Hampshire Hall, which I've been told that room is now called Hanahan Hall. So someone named Hanahan must have left a lot of money to the department. Okay, so 7 people enter the waiting room. This will keep down the feedback. Hopefully you can still hear. It might be one of your computer's sounds need to be turned down.
Mine is muted.
All right. Everybody here okay? Good. Good. Okay, so again, you will see that posted hopefully today, who's going to which room. And again, if there's special needs, I think we've taken care of those. So this is a review. Last time we talked about what happens in these flat surfaces and the fact that when you have this free stream moving and it comes in contact with the boundary, the no-slip condition becomes operative. The fluid at the boundary has the velocity of the boundary, and therefore there's this transition zone where the fluid must go from the velocity of the boundary up to the free stream again. That zone where that transition occurs in the velocity is known as the boundary layer. Outside of the boundary layer, the fluid has no idea that boundary is there. So the fluid, when it is going through this change in velocity, that's a signal being processed in which the boundary is saying, hey, I've got a location where the velocity is 0 here. And that boundary layer, again, is just a zone where the signal is being processed through the fluid. And as you move along the plate, the boundary layer grows. And of course, you know, we can look at finite sized objects, for example, a barge or a plate. Ultimately, when we're talking about a piping system, there is no initial edge and trailing edge, it's a pipe. But the boundary layer exists in those systems as well. And so again, we're building the fundamentals for ultimately getting to this. So again, this is what we're going to see, some type of a velocity.
Mike, how's it going?
when we're in the boundary layer.
Pretty good. I was thinking about picking up some more Xilinx today, or potentially maybe starting a half position in AMD, and I just wanted to kind of get your opinion. Okay.
Excellent. Not that I don't mind hearing your personal conversations, but
Right.
I mind when I'm lecturing. So
Yep.
this is what we have for the boundary layer. And for the boundary layer, again, we have these characteristic
that.
zones. In the laminar zone, the fluid is moving as a nice, straight, structured flow in laminate or sheets. And in the turbulent zone, it's all chaotic flow. In between, there's a transition zone where there's a laminar sublayer zone where you have nice organized movement of particles, and above that is turbulent
Well,
area.
I was about to say,
So
yeah, I
that's
stopped some
really
cache
annoying.
there. I'm just kind of
He's
curious,
probably
what do
not
you,
even
what
listening to
is
the
it doesn't
lecture.
matter, both of them are
keep
good.
sending him a note.
You wouldn't, would you prefer one over the other?
Mute yourself.
Maybe I can mute him. Yeah. Let's see.
Yep. Right. Yep.
Yeah, I just have to find it.
Yep.
Security, no reactions.
If you click on participants, there might be a mute all button.
And what?
If you click on participants, there might be a mute all button. Not sure. There's a mute all button under the list.
Where?
On the right hand side, underneath the list of participants, there's a button that says mute all.
So the,
On the right hand side.
there's
There it is.
Up and over.
a mute
Up
all
and
button.
over.
Oh, no, 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 down.
This
Right
right.
underneath that list.
Mute all. Okay, you can still hear me, right? Thank you. I've never had to do that before. Learn something every day. Good. So let's see if we can get back to the lecture. So again, the height of the boundary layer is delta, and the sublayer, the laminar sublayer in the transition zone is delta prime. And for the boundary layer regions, the laminar region exists up to a boundary Reynolds number of 500,000. And again, this is a smooth plate. We'll talk about what happens when it's roughened. And the transition to turbulent boundary occurs at a boundary Reynolds number of 10 to the 7. And then last time we worked with just the laminar boundary layer, and this is all from the handout last time. And this is what Blasius hypothesized. He developed it theoretically and based it on empirical evidence. And then from that, we could recognize how shear stress delta and any other parameters would vary as you move along the plate in the boundary layer. So again, last time all we did was talk about the laminar zone. Today's lecture, we want to move out of that zone and just look in general, how do we attack these problems that involve the boundary layer? And in general, for the laminar last class, we worked with page, I believe it's 6 of your handout from last time. And for that handout, you had all the equations for all the different layers, all the different zones, laminar, transition, and turbulent. And on page 6, you had this host of equations. And again, almost all these equations come from your textbook. And in fact, in some places, your textbook actually summarizes the first 2 columns for you. What we want to do now is move into the other zones. And how I'm going to do that is with the example that I posted today. So here we have a flat plate, of course. It's in water. It's 2 meters along its length. So again, this distance is 2 meters. And it's 1 meter of width into and out of the slide, into and out of the board, into the other of the paper. And it's being pulled through water, at a velocity of 5 meters per second. So that's the setting. And again, what we're going to be doing is first recognizing that when you do that, you create shear stresses. Shear stresses oppose velocity, and they're acting in the other direction. And if we integrate those shear stresses over the surface, that would give us a force, the force necessary to be pulling this plate at 5 meters per second completely submerged in water. And so again, the first thing we recognize is compared to what we developed, we have a plate and the plate sitting is moving at 5 meters per second and the water is quiescent. And what we do is we become an observer moving with the velocity of the plate. And so this is our plate down here. And we now become an observer moving at the same velocity, 5 meters per second with the plate. And that makes it look as though the plate is sitting still and the fluid is moving over the plate. So again, it fits the basic fundamental theory that we set up for this problem. And for water, again, these are our properties of water. And we did the last problem last class with water, so we're just kind of continuing in the same vein. And in the handout for today, again, there's 5 parts to it. I'm just going to dissect each part and get you to understand how you use page 6 of your handout with all those equations. So the first is, what's the distance along the plate where the laminar boundary layer exists? So remember, the laminar boundary layer exists anywhere the Reynolds number, the boundary Reynolds number is less than 500,000. And the boundary Reynolds number, again, is ux over nu. And x is equal to 0 at the leading edge. And we're trying to find this distance where the laminar boundary layer ceases. Obviously, if you look at the equation for the boundary Reynolds number, u is a constant, nu is a constant. The only thing that changes is x, the distance along the plate. And so obviously, the largest value of the boundary Reynolds number occurs at x, where the boundary Reynolds number is 500,000. So all we really have to do is rearrange this equation and solve for x.
We have a question about what does quiescent mean?
Okay? Quiescent just means it's still. It's like a pond, there's no real velocity. It can be also associated with sound, quiescent. Okay, so this is where we were. And so at a boundary Reynolds number of 500,000, that would be at the farthest extent, x, of where the laminar conditions can exist. So again, the boundary Reynolds number is ux over nu. We just rearrange this equation and solve for x. So when we rearrange the equation, we isolate x. X is equal to the 500,000, the limiting boundary Reynolds number for the laminar zone, times the kinematic viscosity of the fluid divided by the velocity, free stream velocity, which in this case is the velocity of the plate. So when we substitute in the kinematic viscosity of water and we substitute in the velocity 5 meters per second, velocity of the plate, that gives us a distance of 0.131 meters. So in this case, let me see if I have it. Here's our plate and we have laminar and then it goes up like this. And x is equal to 0 at the leading edge. And at x is equal to 0.131 meters, that's the end of the boundary layer. And remember, the plate is 2 meters long. So really, it's really close to the leading edge. You know, it's probably less than maybe 15% of the total length has a laminar boundary layer, and the rest is either transition or turbulent. We don't know yet. That's all we know. So that answers this aspect. One simple question. Is there a laminar boundary layer over the whole plate? Of course not. It only exists in the first 0.131 meters. The rest of the plate, boundary Reynolds number grows. So the rest of the plate has a boundary Reynolds number greater than 500,000, which means it's transitional or possibly turbulent. Part 2. what is the thickness of the boundary layer? And again, the boundary layer total thickness is used, we use the Greek letter delta at x is equal to 0.1 meters, 1 meter, and 2 meters. So again, this is our operative sketch. And we have a plate where x is equal to 0 at the leading edge. We want to know what the thickness is at 0.1 meter. At 1 meter, and when x is equal to 2 meters. Let me change that color. So that's the question. And again, the key to solving any of the equations in the boundary layer section is to know the boundary Reynolds number. On page 6, all the equations are organized by boundary Reynolds number. Is it laminar? Is it turbulent? Is it transition? That's the key and the secret. You need to know the boundary Reynolds number first. So again, we want to know the size of the boundary layer. That's delta. This page, you're going to see it a number of times today, is from page 6 of your handout. And so we have an equation for laminar. We have an equation for transition. And we have an equation for turbulent. We don't know which equation to use until we calculate the boundary Reynolds number. So with that in mind, for delta, we need to know the boundary Reynolds number. And so from the last sheet, page 6, from the last slide, page 6 of your handout, if we have a laminar boundary layer, this is how we calculate it. And if we have a transitional boundary layer, this is the equation to calculate it. And at the end of this lecture, I'll discuss how they arrived at all these equations. But this is from page 6 of your handout. It's the page we just looked at on the last slide. Same equations. So on your handout for today, the first column is the distance. These are the 3 distances you were requested to calculate the thickness of the boundary layer. Second column, the first thing we do is calculate the boundary Reynolds number at each of those locations. Again, the boundary Reynolds number is at the top of this slide. The free stream velocity we know, 5 meters per second, and the kinematic viscosity of water we know. And so all we do is change, we put x into that equation, and that's how we came up with column 2. You already know that at x equal to 0.131 meters, REX is 500,000. That was part 1. What's the distance of the laminar boundary layer on the plate? So point 1, we should see that at x equal to 0.1, we have a boundary Reynolds number less than 500,000, and we do. And so it's laminar at that first point. When x is equal to 0.1, the boundary layer is a laminar boundary layer at that point. Questions? Good. So if we look at those 3 rows for the boundary Reynolds number, at x is equal to 0.1 meter, we have a boundary Reynolds number of 381,700. That's less than 500,000, so we have a laminar boundary layer at that location. At location 2, where we have x equal to 1 meter, we have a boundary Reynolds number of 3,820,000, 3.82 times 10 to the 6. Question, is that greater than 500,000? Yes, so it's not laminar. Is it greater than 10 to the 7th? No. Since it's between 500,000 and 10 to the 7th, you have a transitional boundary layer at x is equal to 1 meter. Does everybody understand that? I want to see responses in that chat room. If I don't, I have to slap the TAs.
Now they're on.
Oh, okay, you're saying they're all responding? That's good. At
Well,
the-
Sansa, can you repeat that?
Sure. Since I was asked if I can repeat that, do you understand how to calculate the boundary Reynolds number?
Yeah, yes.
Yes. So remember,
Yeah, is it 10 to the 7th or 6th?
that I'm bringing up that figure. So. There it is. So for the first one, at x is equal to 0.1 meter, we got a value of 3.8 times 10 to the 5th. That's less than 500,000. It's laminar. For the second one, we got 3.8 times 10 to the 6. 2 meters at 1 meter. So the question is it greater than 500,000 or less than the 10 to the 7th? It's in between the two, so that's a transition boundary layer at x is equal to 1 meter. I'm going to go on, but tell me if that answered the question. Actually, I'm going to stay on this slide. In the table on your handout for today, at x is equal to 2 meters, the boundary Reynolds number is equal to 7.63 times 10 to the 6. That's also less than 10 to the 7. So at x is equal to 2 meters, you also have a transitional boundary layer at that location. So this is where we were. And again, at this last distance, we know that we have a transitional boundary layer. So when when the boundary Reynolds number at x is equal to 0.1 meters is 381,700, this is how we calculate the boundary layer thickness in a laminar boundary layer zone. The boundary layer thickness is 5x, in this case, x is equal to 0.1 meters, divided by the boundary Reynolds number, 381,700 to the 1/2 power. And that gives us 0.809 millimeters. At the other two locations, at x is equal to 1 meter and x is equal to 2 meters, we have a transitional boundary layer. If you go to your handout again on page 6, these equations for the thickness of the boundary layer are organized by laminar, transition, turbulent. So if you go back to that handout, you will see for the thickness of the boundary laminar, for the boundary layer in the transition zone, delta is equal to 0.16x over REX to the 1/7 power. X is equal to 1 meter or 2 meter for the last two locations, and REX are the respective Reynolds numbers. And so what you see is obviously in this case, the boundary layer is growing from x is equal to 0.1 meter to 1 meter to 2 meters.
I have a question. This is, do you multiply the x value by 2 like we did when both sides were submerged?
Okay, are we talking about a shear force? No, there's no 2, it's not about sides, it's where you're located on one side. So this is the boundary layer, and if this is on the top, the same thing is happening on the bottom. At 1 meter along the top, the boundary layer is 18.4 millimeters thick. If you go on the bottom side, at 1 meter along the bottom, the boundary layer is 18.4 millimeters thick.
And then, someone is saying, thickness refers to the thickness of the liquid above the plate, correct?
The liquid is infinite. The boundary layer is a zone in the liquid where the velocity is going from the velocity of the plate to the free stream velocity. In the relative sense, the plate is sitting still and the fluid's moving by it at 5 meters per second. And this boundary layer, for example, at 1 meter, is 18.4 millimeters thick, where the velocity goes from 0 to 5 meters per second. The rest of the fluid could be tens of meters deep, has no idea that boundary's there, and it's all moving at 5 meters per second. In the real system, the fluid is sitting still, it's quiescent, and the plate is moving through it. And so what you see is the fluid sitting still, and at an instant where you take a snapshot of the plate's moving at 5 meters per second, and the velocity profile is going from 5 meters per second back to 0. Okay. Good. So this is still example 1. And again, what we have in this problem is we have a section of laminar, and that goes up to x is equal to 0.131 meters. And the end of our plate is x equal to 2 meters. And at the very end, we just have transitional boundary layer. So we have no turbulent boundary layer on this plate. It's too short or it's moving too slow. We did not get a boundary Reynolds number anywhere on this plate greater than 10 to the 7th. If we did, at that location, we would have a turbulent boundary layer. Okay. Is that the end of the world? Of course not. It's just the characteristics of the boundary layer on this flat plate. Okay, so that was just part 2. Part 3, and again, this is all on your handout for today. Part 3 is, what's the boundary shear stress? Tau 0 and x is equal to 1 meter. So again, what we have is this plate. And if I put it in perspective, this is the laminar. And this is the transition. The laminar is only over the first 0.13 meters of the plate. And so the question is, at 1 meter, what is the shear stress at that location? As you move along the plate, it changes. Why? Because remember, shear stress is related to the velocity profile, du dy. And as you move along the plate and just stay where y is equal to 0, right at the plate surface, that velocity gradient is changing everywhere. So we're asking a specific question, what's the shear stress right at this location? And it would be the same on the top as it is on the bottom. Okay. So again, at 1 meter from the last problem, we have a boundary Reynolds number of 3.82 times 10 to the 6th. That is a transitional boundary layer at that location. And why that's important, I've said this a few times today. In order to solve these problems, you need to know what the boundary Reynolds number is. Why? Page 6 of your handout is organized based on what type of boundary layer you have. You have the variables on the very left-hand column. We're after shear stress. And depending on what type of boundary layer you have, in this case, you only see equations for laminar and transition. Ultimately, as you move out of transition into turbulent, it basically is a very similar equation. So we need to know where we are. And because at 1 meter, we've already calculated that the boundary Reynolds number is 3.82 times 10 to the 6th. We know at 1 meter, it's a transition boundary layer. This is the equation we will use. When we use this form of the equation, this is the theoretical form. If you recall from the last lecture, there is a momentum form of the equation as well to get shear stress. And so the shear stress coefficient, CF, is calculated again on page 6. We just need to know, is it laminar, transition, or turbulent? We already know at x is equal to 1 meter, the boundary Reynolds number is 3.82 times 10 to the 6. It's a transitional boundary layer. So if you're using the momentum form of this equation, that's the equation you're going to use. I'm going to do both. We should get about the same answer. There's always a difference when you go from theory to practice, though, because it's in how well they calibrated little CF, the shear stress coefficient, as it's known. So part 3, again, we want to find tau 0 at 1 meter. So let's first look at the theoretical equation. Because we have a transitional boundary layer, again, if you go to page 6, this is the equation you will see for the shear stress at the bed, at the boundary, tau 0, in the transition zone. We know we're in water, so we know the density of water. U is the velocity of the plate in this case, the free stream velocity in the relativistic sense, 5 meters per second. And REX is the boundary Reynolds number at this location. X is equal to 1 meter. And as we already know, that's 3.82 times 10 to the 6th. So we substitute everything in there. And what shear stress has the dimensions of pressure. So what we get is 40 Newton per meter squared for the shear stress at this one location. It's the same value on the other side of the plate at x is equal to 1 meter. Any questions on that? Good. So the second form of the equation is the momentum form of the equation. And the momentum form of the equation says that the shear stress at the plate is equal to, and this is true anywhere, whether it's transition, laminar, or turbulent. That's the beauty of the momentum equation. What you have to, the challenge though, is the shear stress coefficient is a function of whether you're in laminar, transition, or turbulent. That's the key difference. So in this case, again, from page 6, and at x equal to 1 meter, we know we have a transitional boundary layer there. The shear stress coefficient, little cf, for the transitional boundary layer is equal to 0.455 over natural log squared 0.06 REX. You know what the boundary Reynolds number is at this location, 3.82 times 10 to the 6th. We've already calculated that. And so we can calculate this shear stress coefficient, 0.00299. And that then would go into the shear stress equation up above. So we know the shear stress coefficient now at this location. We know the density of water, and U is again the velocity of the plate, or in the relativistic sense, the velocity of the fluid moving over the stationary plate. So when we substitute everything in there, we get 37 Newton per meter squared, which is close. It's not exactly the same, but again, that's the penalty you use, you get when you move between theory and empirical data. If you're asked to do this on an exam, pick one. You don't have to do them all. If you pick one, run with it. Because essentially they're supposed to be the same. Any questions on that? Excellent. Fourth part of this example. What's the frictional resistance due to shear, in this case, the drag force on the flat plate? And again, the momentum form of this equation looks like this. The shear force, or in many cases, it's called the drag force, capital D, 1/2 times capital CCF, that C sub F, that's the drag coefficient. And you have a figure of this in your handout, and it's the same figure in your book. And I'll bring that up. Times the density, times the cross-sectional area. This is where the two sides come in. When you're integrating the shear to get the drag force, you have to integrate it over the entire surface area. This is the only place where two sides comes in. Times the velocity squared. So CF from page 6, and we're going to see page 6 on the next slide, depends on the boundary layer characteristics you have. Because we're talking about this drag force, to get the drag force, we integrated the shear stress over the entire surface area. And therefore, what pops out of that integration is the boundary Reynolds number at the trailing edge. So when we set X equal to the total length of the plate, we're calculating the boundary Reynolds number at the trailing edge. REX becomes REL. Boundary Reynolds number at the trailing edge at X equal to L. And in that case, for C sub F is going to depend on, C sub F is the drag coefficient, depends on the boundary Reynolds number at the trailing edge. So it doesn't matter that you have a laminar boundary layer at the leading edge. It's whatever that boundary layer characteristic is at the trailing edge that's going to dictate the drag coefficient. So from part 2, we did calculate the boundary Reynolds number at the trailing edge of X equal to 2 meters. We calculated that the boundary Reynolds number at the trailing edge was 7.6 times 10 to the 6. That's a transitional boundary layer at the trailing edge. It's less than 10 to the 7th. So, how many times have you seen this today already? This is page 6 of your handout. We're interested in the drag coefficient. The drag coefficient has one way to calculate it in the laminar, another equation in the transition, and yet another equation in the turbulent. And if you look closely between transition and turbulent, in the turbulent, you just lose that last term. That second term, 1520 over the boundary Reynolds number, as the Reynolds number gets larger and larger and larger, that last term is going to 0. So again, for many of these variables that don't have values in the transition zone, a lot of it is because the equation that's used in the transition carries out more or less into the turbulent zone. So in this case, this is the equation we're using because we have a transitional boundary layer at the trailing edge. You cannot solve these problems unless you know the boundary layer characteristics. And every part that we've done in this problem, the first thing we do is calculate the boundary Reynolds number. That unlocks the equation you need to use on this Rosetta Stone. If this is one of your sides of your crib sheet on the final exam, that's fine with me. All of these equations are in your book. So for the drag force, this is our drag coefficient from the previous page. And the only thing we need to know is the boundary Reynolds number, which again is 7.63 times 10 to the 6th. So when we substitute that boundary Reynolds number into this equation, we get a value of C sub F of 0.00288. And it's just coincidence that it's very close to what little c sub F, that was 0.00299, if I recall from the previous one. Let's see. Yeah, it was 0.00299. It's just coincidence they're that close. I just want to underscore that. So now we can take that drag coefficient, put it into the drag force equation, and calculate the drag on this flat plate. And again, this is where we have to recognize we have two sides. So the area of one side is 2 meters by 1 meter. Since this plate is completely submerged, we have to make sure we account for both sides. In some of your problems, the plate is only submerged on one side. For example, the bottom of a barge, or it's the outer shell of a train. So in this case, we're substituting all that information into this equation, and we get a drag force of 144 newtons. Are there any questions on this one? So again, everything here has been copy and pasted from your handout. So I was trying to make life easy for you so you could just annotate on your handout. So this is on page 5 of your handout. It's the drag coefficient on the vertical axis, C sub F, versus the boundary Reynolds number at the trailing edge, REL. And this is figure 910 in your textbook. And in this particular example, we have a boundary Reynolds number at the trailing edge of 7.63 times 10 to the 6th. Go up to your curve, go over, and you read out 0.0029. We calculated 0.00288 when we calculated it. So this is a nice little check on what we just did. And again, here's the same equation that we used, and you can see that equation is used on this part of the curve. And elsewhere on the curve in the laminar region, we're using this equation. And that's the equation we used last class when we were looking at the laminar region. So there are different equations which describes this. We only have 10 minutes left, but I'll see if I can broach the topic. We've been discussing everything up until now is smooth plate. Is everything a smooth plate? Of course not. You can artificially roughen, or some surfaces are roughened. And when it's roughened, you, at the very leading edge, you cannot maintain the laminar boundary layer. And again, a lot of times we intentionally do that. And therefore, there are different equations if you've tripped or artificially roughened the surface. So this has everything to explain, again, sharp surfaces are roughened. Next time you fly in an airplane, the leading edge of the wings is roughened. Golf balls are dimpled. There are many, many reasons why we're playing around with the boundary layer to get certain performance characteristics. So at the very end of this lecture, I'll talk a little bit about tripping the boundary layer. But on page 6, you will see this same equation for the drag coefficient. So the last question in this example today is, what's the necessary power to pull the plate through the water? And this is the same as last class. We did the exact same calculation last class. Power is force times velocity. So we know that we just calculated the drag shear force of 144 newtons. The plate velocity is 5 meters per second, and that gives us 720 Newton meters per second, which is 720 watts, which is 0.72 kilowatts. So again, this one, you don't see the fact that you have a transitional boundary layer at the end. That was all built into the drag force, Fs. But it ultimately did depend on what that boundary layer characteristic was, the trailing edge. So this is also in your handout, and it's the last page of your handout, and it's also a figure from your textbook. In case you were forgetting what it looks like, this is what your textbook looks like, and this is a figure right from your textbook. And this is basically a velocity profile. So you see U on the horizontal axis and Y on the vertical axis. However, it's been put in a dimensionless form. So U over U star is known as the shear velocity, and it's equal to tau 0 over rho. And then you see kinematic viscosity and U star also on the vertical axis. And whenever you see the same variable on both axes, you run the risk of, in statistical nomenclature, spurious correlation. So I won't go into that, but again, this is a classic diagram. And why I bring it to your attention, where you see the yellow highlight lower left, that's laminar. These are the Blasius equations, whether you know it or not. You will see these other highlighted areas called the logarithmic velocity distribution. And you can see the equation for the logarithmic velocity distribution up here. This is used a lot in streams. And then you see something called the velocity defect law. And the reason why I bring these to your attention, if you go to the bottom of page 6, for velocity, there are the 3 columns: laminar, transition, turbulent. This is the log velocity profile. This is the 1/7 power law. which I didn't call out, and this is the velocity defect. Why do we care about this? This all goes back to what Blasius did. In the laminar zone, once we know the velocity profile, we know shear. Shear is equal to mu dV dy. You need to have a velocity profile before you can get to all these other terms and the thickness of the velocity profile. So many people have spent their careers just trying to figure out one of these profiles. Probably the two most popular today are the logarithmic velocity profiles and the 1/7 power law. The logarithmic is probably a little more adaptable, and the 1/7 is easy to integrate when you're doing theory. So, those are the classic ones. So again, on the bottom of page 6, you will see these equations, and I put them there so you can have some idea of how people get all these weird looking equations above. If you look at some of the equations on page 6 for some of those variables, you will see the boundary Reynolds number to the 1/7 power. Where on earth did that come from? The 1/7 power law. And again, theoretically, it was easy to integrate something like this and tease it out of the equation. So in your careers, you probably never have to worry about this unless you go into specifically this field. But it's helpful that you at least can recognize some of the rudiments that you see in some of these different equations. So I wanted to bring that to your attention. And again, all of this information appears here on page 6. So tripping the boundary layer in the last few minutes. Your book used to cover this and now it doesn't. Although it has a little section where it says roughened surface, which is a tripped boundary layer. So some problems will say for a roughened flat plate, you know that is a tripped boundary layer. And I'm going to explain what that is. But we know the boundary layer thickness anywhere along the plate is delta. And to maintain particularly the laminar zone, laminar means you've got nice structured flow. You need to have a very smooth flat plate. But what if you had roughness elements that look like this? It's impossible for the flow to stay nice and flat when it has to go over a mountain or around one of these mountains. And so we'll either call the roughness element size case of S or K, lowercase, okay? And when we want to artificially roughen the surface, basically what we're trying to do is avoid any laminar characteristics from the leading edge on. And so what happens is if you create turbulence at the beginning of the flat plate, it's turbulent for the rest. The laminar sublayer or any laminar boundary layer cannot reestablish once you have the turbulence. So again, characteristically, this is what we're talking about. From the leading edge, we're going to put these roughness element characteristics. And fundamentally, if the relative magnitude of the roughness element compared to the height of the boundary layer, if the roughness element is incredibly small, that's why you see two inequalities here, then that's considered hydraulically smooth. What we have to do is come up with a number for that. And in the opposite, if the roughness element is larger than the boundary layer, then there's absolutely no way you can maintain a laminar condition. The real crux is, well, what if you're between those two, like I drew on the last one? What if the roughness elements are actually smaller than the boundary layer? So we can actually calculate a critical roughness element height. And this has been done by theory. I'm just giving you the equations here. But depending on where you are, what you can do is calculate what that critical roughness element height would be. If you really want to be conservative, the largest the laminar boundary layer can be is where the boundary Reynolds number is 500,000. So obviously, if you look at this equation, the critical roughness element height is directly proportional to the boundary Reynolds number. Just put in 500,000. And if then you have your flat plate, and this might have been the laminar boundary layer, how it grew. In this case, if you put in these roughness elements, KC in height, you will not be able to have that boundary layer. Instead, what you will have is a turbulent boundary layer from the beginning, and that turbulent boundary layer would look something like this. It's actually smaller. And the reason for that has everything to do with molecular momentum exchange. In laminar flow, the ability for particles to move up and down and impart momentum is much less than in turbulent flow where the fluid's already moving in 3 dimensions. And so you don't need as much of a boundary layer to have the signal processed. What's the signal? Hey, at the flat plate, the velocity is 0. That's always the signal being processed. There's a boundary somewhere. So I think I've covered the boundary layer. Yeah, that was the last slide. Are there any questions in the remaining 30 seconds? So again, all this stuff is on exam 3. Do you need to know everything from exam 1 to do this? Not really, but you do need to know what fluid properties are: density, kinematic viscosity, viscosity. So it's not a cumulative 3rd exam. It's just an exam on the topics we're starting Monday, yesterday, right through the last day of class. And the 2nd exam is from acceleration of fluid masses through momentum. No questions?
There is one question.
Yes.
I don't understand what you're asking. When it's significantly greater than 1, what was it labeled as?
What?
It says when it's significantly greater than 1, what was it labeled as?
Well, if K is much greater than the height of the laminar boundary layer, it's just a roughened surface. And if K is much less than 1, it's hydraulically smooth. It's in between, what are we going to call it? Well, it could be roughened if your critical roughness height looks like this. And again, you'll see when we move forward into drag, which is what we're going into next, 3-dimensional drag, there are reasons we actually do this. All right, so now I'm over. So I'll let you go and I'll see you Friday. And we have a review session Thursday. It's all online.